Okay, everybody. Let's get started. Okay. So welcome to Statistical Machine Learning class 2021. Okay, I'm glad right now that about 60 of you have dialed into this online meeting. Because we can't have like a large-scale conversation in real time, can I have a few confirmations in the chat channel if you can hear me and see me okay, and see the screen as well?
Yes, I can hear you.
Great, thank you. So as you know, we are recording this meeting for the rest of the class, and I'm also experimenting streaming to YouTube. Yep, okay. Yep, thank you for the verbal and also chat confirmation. I think, so I assume this works all right. Yeah, in case at some point the connection becomes bad or you can't hear me anymore, feel free to speak up, or monitoring the chat channel in real time is hard. But in case something breaks, we'll try to make that happen. Right, so for the, as of this morning, the statistical machine learning class has broken a record. There are over 200 students registered. I would say that this semester will be the first. Myself and 7 tutors handling a class of such scale. It has grown by about 50% since last year. It will be your first of basically a tour of in-depth machine learning in depth, whether or not you have taken an intro to machine learning class. And online learning is new to a lot of us.
I can't hear you now.
Yeah, me too.
I think you're on mute.
Oh, yep. Okay. Can you hear me now? Yes. Great. Okay. So the two main things we will cover today is how basically the logistics of this class, which will be the same as if we were running in person, and also a few words about how we are going to run this in blended mode. I hope this will take less than half an hour. And then the next half an hour, we will talk broadly about the scope of the class in relation to what machine learning is and what are the main challenges and the current challenges. Basically a broad overview of the field, if you will. So let's get started. First of all, this class, let's use the acronym SML from now on. Is a few years ago, the official class name is Introduction to SML, which I think is still very much appropriate. The focus of this class, as you might have read in the class homepage and program courses, is to cultivate mathematical thinking in machine learning, to look at the rationales and, of behind models. We will delve into derivations and implementations of a broad set of models. Walking away from this class, we hope that you will also acquire in-depth appreciation and critique of how to design models and what models should be used when. Note that this is the second in the sequence of machine learning classes that's available in computer science. In the pre-class survey, about 2/3 of you have taken the Intro to ML class. So you will gain one more step of deeper understanding from that. As you will see from the next lecture onwards, and at least from next week onwards. And going forward from this, there is an option to take advanced machine learning, which focus on optimization and a few other in-depth selected topics from here. And for another third of you, this may be your first encounter to machine learning. So there will be some content tailored to that. And over the years, we're hoping to sort of make IML and SML work more seamlessly with each other, and we'll be gathering feedback. And generally in the AI and machine learning space, there are these other classes that are not directly in sequence. For example, in document analysis, people will be using machine learning components for natural language processing. In the optimization class, especially the continuous optimization part, is quite closely connected to different models we will be talking about. For example, if you would like to know what are the different gradient descent techniques are there and different kind of optimization techniques for non-convex functions, it's quite relevant. In the new network science class, there will be various components that cover probabilities for large networks, and also machine learning, touch upon machine learning on graphs, data, and networks. In the AI and advanced AI pair of classes, what is relevant to machine learning? So advanced AI currently, or as offered last year, has coverage of reinforcement learning and what's called PLOM-DP, or partially observed Markov decision processes that are, I think, currently considered as part of the umbrella of machine learning. If we take the machine learning centric view, right? If you take the planning centric view, if you've taken AI, then it's also part of planning. So labeling is not so important. So this is basically where SML sits in the broad scope of AI and machine learning curriculum. This is an overview of the team who will be helping you. So this is me. And then we have 7 excellent tutors. 6 of them have tutored XML before. One of them new, but is also a very experienced tutor. So for those of you who have watched the introductory videos, 6 of these tutors appears on the videos and talk to you about what they're working on, what their advice is for this class, and what their favorite machine learning model is. So I highly recommend that you watch them. So this class has been developed by a group of researchers over the past more than 10 years. So Chris Weber, who is a researcher at Data61, originally developed it. He will not be involved in this class nor make an appearance. Ching-Song Ang, some of you might have already known or heard. He is the author of the Mathematics of Machine Learning textbook. He also taught this class for a few years. And Christian Wilder is the main voice in videos. of recorded lectures from the previous years. So he was the lecturer from last year. So you will have heard about them, and here's what he looks like. So again, so here is the introductory videos of tutors, and you guys, since a lot of you are studying remote, you're welcome to upload one of these to Piazza to talking about yourself, and get the class to know you if you need teaming for assignments. So because this class is delivered in a blended mode, or during the lectures, we will be remote. We won't be in one room. Here's the technologies we will use. Most of you would have seen the class website. For example, there is an assessment page that details what you're responsible for. It's mainly read-only information. And then we are currently on Microsoft Teams, which we will be using to hold what we call workshops like this and tutorials. Piazza, as most of you are familiar, are for text interactions. Grayscope will be used for assignment submission. We have tried Grayscope in the previous classes that I have taught. From both the tutor and lecturer perspective and student perspective, it provides better feedback for your assignments, and it also improves the communication between students and lecturers. So to be more concrete, by better feedback, I mean that tutors will more easily give you feedback on each and every question, rather than typing in one brief text blurb for your whole assignment, as in the case of Wattle. So Wattle will be used to, like you can use those as an entry point to view recorded lecture videos from 2020. And it's also used for lab sign up that some of you have seen will open from noon today. Right. A few more words about what we're doing now versus recorded lectures. So here's the rationale and what we will be doing, right? There are pre-recorded videos from last year's, each of them about 1.5 hour long, from various feedback from tutors and students that we have received. In that watching the 1.5 long video from end to end might be difficult. Therefore, we decided to sort of supplement the lecture with these workshop sessions that are less formal, and the content will be more or less the same. When it's different, I will indicate that. And the focus of Okay, thank you. The echo is gone now. The focus of the workshops will be covering the rationale behind some of the mathematical formalities, and then also will be basically providing a view that's complementary to the videos and also the textbook reading. What this also means is that we firmly believe that learning is done by you, and the lecturing and tutoring are here to help. We're not here to actually essentially impose the material in you, right? And our job is to help and then check your understanding with the assessments. So as an example, the notes for this Friday session is already posted to the Microsoft Teams under the Files section. So let me see if I can get to that. So we're still working on exactly what content sits where. Okay, does it show me files? No. Anyway, we can get, okay, we'll get to that. Basically, in some of the sessions, the notes will be quite different from the slides. In some of the sessions, will be about the same. And when there's annotations during the workshops, I'll post the annotated version. So we've already decided on the slots. So basically Monday 10 a.m. and Friday 12 noon is the preferred slot. And then in addition to that, we have 9 tutorial sessions each week to help you go through the practical materials and address any more questions. 4 of these will be in person, and then 5 of these will be online. So let's talk a little bit about what you are expected to be responsible for. Assessments. It's exciting, always exciting content for each class. Okay, so here are the assessments that you're accountable for. The first few items up to the final exam is obviously important. In roughly week 5 or end of week 4, you will have an online quiz. We expect it to be a number of, say, a dozen or so multiple choice questions. It counts for a little bit, and the questions will be more or less bespoke, and it checks that you're engaged and are comfortable with the basic material in the first few weeks. We will have more details about that closer to time. And the main assessment items include 2 assignments that are a mixture of what we call theory or mathematical reasoning and derivations and proofs, and also practical components in a way that's somewhat similar to the tutorials and labs that you go through each week. So they cover the first and second half of the material respectively. The first assignment will be released next week. In addition to that, we will have 1 video assignment as a special of blended learning, meaning you will pick content from one of these assignments and talk about it. And the tutor team will essentially grade your presentation, so to speak. And we will also release more, basically some structure about that, expectations and what you're expected to cover closer to time. There will be a final exam. As some of you might have done this in the last semester, it will be done online. You'll likely get emailed or will disseminate exam paper beforehand, and you'll have likely about 3 hours to complete it. It will count for 30% of the mark rather than 50%, if we were in person. So the 2 written and programming assignments can be submitted in pairs of your choice with another student, or you can go solo, that's fine as well. And here is basically spelling out the expectation of paired assignment. And then for the video assignment, there's brief specs about how long we expect this to be. There's some wording about lay policy. Basically, you can be, if you're within 1 day late, there's a 5% penalty. And if the submissions made more than 1 day late will not be accepted. The submission system at Grayscope will close. So that's briefly that. So again, we're studying in most unusual times. We have gone through most of this. Don't need to. So you're encouraged to work together and encouraged to come to the tutorial sessions to have a discussion with the tutors. And the prerequisites of this class are basically the assumed knowledge will be knowledge in basic probability. In the next lecture, we'll go through some of the key probability concepts, but it's not a replacement of people having already know some of it, right? In the book, it calls it probability theory. I wouldn't call it that way. It's basically probability applied to data, as we will see, and also linear algebra. So across the ANU undergraduate courses, I think the entry-level courses covers matrix multiplication, but not the subsequent items. Hopefully you have taken one of the other courses that covers eigenvalues, solving linear systems, matrix inverse, and so on. If you haven't got these concepts, hopefully you can brush them up. The assignments and labs in this class are done in Python 3 via Jupyter Notebook. So this week's lab or practical component is basically asking you to set up Python in your laptop and play with it. So this class is mathematically involved, but it's also rewarding in this sense, and we hope you will make the effort and enjoy the ride. So I've posted basically a preparatory assignment. It used to be given as a entry hurdle assignment, but we are happy to leave it to you. You're all third-year students and up. So take a look at that assignment. So you should be able to crack more than half of the questions with a little bit of effort, hopefully. And not all of the questions are of similar difficulty. So some of, at least one of them is more difficult than usual. So if you don't get them all, don't panic. So let's have a look at since there will be no lab this week. So if you go to the week 1 page of the class website, you will see, well, there's a tutorial section here. It says Introduction to Python. You can download a notebook. We're looking at the HTML version here. So basically, introduction. This is what Jupyter Notebook look like. You're asked to write some math. Basically, in the markdown cells, you can write mathematics using LaTeX symbols. These are to check that you can do this, and if you don't, spend half an hour brushing up on how to do so. It also basically echoes the content of basic probability that we'll cover on Friday. There's some calculus, and then here's the programming component to check that you have Python 3 and the required packages, NumPy, working essentially. Here is some markdown content. If you're not exactly familiar with LaTeX and writing formulas, double click on these cells and it will expand it for you to tell you what basically the basics of writing math in LaTeX look like. Of course, you can use Google and Stack Overflow to help you. And here, you're asked to generate a toy data set and read and write some data in CSV format. So these may look naive, but I would argue that in machine learning, being able to generate and demonstrate the workings of a model on an appropriate toy dataset is one of the key skills of machine learning research and application, so to speak. Many people think that being able to do machine learning means being able to whack fancy machine learning models on massive data sets, say from the internet or from, like, if you're in industry, in real data. But in reality, you have to make sure that your models are correct, and the way to check that they're correct is not with say, a data set of 1 million rows from a customer database. Instead, it is, well, do your code, generate a toy data set where you know what the expected results should be, and then run your code against that. So you will, I think this is a good segue to our next content, basically what the book will do, right? Throughout the textbook, there are many illustrative examples of here's how we generate a small data set or a toy data set that's naive looking and using, and here is what it really tells you how the model works under the hood. And this is one of the things that I appreciate about this book, and certainly not the only one. So our textbook written by Chris Bishop in 2006 is what we will follow pretty closely. We will only be able to cover a subset of sections in this book. In my opinion, it is, you might think, oh yes, machine learning has developed a lot in the last 15 years. Why are we still using this book? I feel, well, one needs to cover the basics, and also this book is quite well written. It has sort of a flavor or emphasis on Bayesian methods. Not all of that we will cover, but I think it is also good in a sense that it really starts out by preempting lots of the advanced methods. So I'm hearing echo some of your muted. Can people check that? Yep, okay, that's gone. So as we will see later this week and next week, this book starts by talking about linear regression in a kernelized way, which is great in two senses. One is it gives you an advanced understanding of linear regression beyond intro to ML. And also it preempts the kernel section much later on. The book is free, as most of you already have known, in PDF. So that's another good incentive for covering it. So besides this book, there are many good choices of machine learning textbook out there. Those of you who have taken IML would have known this, what's called MML book, Mathematics for Machine Learning, that covers basically a smaller set of approaches, and it's more recent. And then there is Kevin Mersby's book. I'm showing the cover of the last version. The new version is freely available online and will be released this year. The Kevin Mersby's book is, I would say, a lot thicker. It's 900 pages rather than 600, and it covers more content, sometimes in more depth. So I think that book is, in my opinion, a bit too much for a course like SML, but it is a good book. So for some of the content, if you want a different view or deeper view, feel free to go refer to that. We might occasionally refer to these textbooks. For example, we do plan to cover a little bit of automatic differentiation from the MML book. So here's basically our logistics section. Let me pause here. We're exactly at half an hour. Let's say we take questions for 3 minutes if there's any. If not, we move on. Feel free to unmute and cover questions.
Hi.
Yes.
About the video assignments, do we need to submit a recorded video assignment, or we need to attend some workshop and give a live presentation?
Great question. Thanks. Yes, for the video assignment, you are expected to record yourself talking, and then submit it in one of the platforms.
Oh, thanks.
Yep.
Do people working the same like paired assignment? Do they have to go to the same lab as well, or is it going to be in different lab?
The short answer is no. People can be in different labs and they can still submit in pairs.
Okay, thanks.
Yes.
Hello.
Yep.
I had a quick question. If we do a paired assignment or we do it by ourselves, is the content of the assignment exactly the same?
Great question, thanks. Yes, it is. So people will work on exactly the same assignment, no matter whether they fly solo or are paired. When people are working in pairs, in Gradescope, there's an option to submit a paired assignment. You can just say, well, this is done by the two people, and with a brief statement about who did what. And that's for sanity checking. And the two people in this, like submitting the same assignment, are expected to get the same grade, unless in extreme cases. All right.
Thank you.
Thanks.
I had a question about the hurdles. Like, are any of the assignments or the exams any hurdles or?
Oh, hurdles. As we said a bit earlier, in here, when the screen share comes up, yes. Yeah, I guess it doesn't allow me to draw, but basically the first item on the online quiz is a hurdle. It's only 2%. And the expectation is as long as people are sort of somewhat engaged in the content for the first 4 or 5 weeks, they should be able to pass the hurdle. I hope that helps.
Yep, thank you.
Yep. Okay, if there's no more questions for now, let's move on. So in this second half of this session, we're going to talk about what is machine learning, a simplistic categorization, and later on a more elaborate categorization, and what those means. Some of you might have heard of at least supervised learning in IML and maybe a bit more, and also like dimensionality reduction, but it's machine learning is more than that. And also biased samples about what contemporary machine learning research projects is like, biased towards what's happening here in my lab and the rest of the computer science department. We will also touch upon pressing concerns in the fairness, accountability, and transparency of machine learning algorithms. So I would basically start by saying that as computer scientists and designers of machine learning models and programmers of machine learning models, we cannot shy away from the responsibility to ensure that ML algorithms are fair, accountable, and transparent. It's an ongoing challenge, and it's also an exciting time to develop a career in this space. So we also will say a few words about what we will and we will not cover. And hopefully we will stay in time. So there are multiple definitions of machine learning. We're just going to select 2. So Arthur Samuel, in 1959, famously said that machine learning is the field of study that gives the computer the ability to learn without being explicitly programmed. So that's quite an lucid definition that still applies today. What does this mean? So before this, or in programming 101, you are asked to program, let's say, a robot moving left or right, or a set of rules of a game, or a set of rules based on which your agent will search in order to win the game. But as Samuel's work, what's shown in the checkers program, you basically observe sessions of checkers that win or lose, and then train an agent to play checkers. Right? Well, checkers is sort of an important program in machine learning because the first reinforcement learning practical algorithm was also developed to sort of self-play checkers and then eventually win and beat the humans. So the second definition of machine learning that we will mention is one by Tom Mitchell, a professor at CMU. He said that a computer program is said to learn from experience E with respect to some class of task T and performance measure P. So if it's said to be learning if the performance at task T as measured by performance measure P improves with experience. So this one basically makes Arthur Samuel's definition more concrete. There are three elements: task, measure, and then experience. Or in our lingo, so experience usually are encoded in the form of data, and performance measure is encoded in loss function and evaluation metric. The two of them ideally are the same thing, but sometimes are not. And the task T is, in the case of supervised learning, encoded in the like classification targets, right? So here's the, in terms of the checkers, the data or experience is games played by the program itself, and the performance measure is the winning rate. So that's easy to understand. So since 1959, machine learning has gone a long way, right? Or actually even before that. So the perceptron algorithm that we now know as a building block or primitive building block of neural networks was first developed by Rosenblatt in 1957. As we will see in, I think about week 4, the first perceptron algorithm is actually implemented in hardware. Fascinating. So in 1980s, artificial neural network developed. In the 1990s and 2000s, statistical machine learning have developed a lot. So the new approaches from that time was kernel methods around 2000, decision trees, graphical models, and so on. A lot of what we learn in this class is developed in, let's say, the last 20, 30 years. And I think nearly within the lifetime of most of this class, which is an exciting thing. Unlike in, let's say, university math classes in your first and second year, a lot of it is developed a lot earlier, right? And what has propelled statistical machine learning in the last 20, 30 years is not only the mathematical ingenuity of researchers working in this field, where this field broadly means, well, computer science, and people from statistical physics, statisticians, and so on. It also means the reason that SML is distinct from statistics is also in the way that it's intertwined with computation, right? For example, faster computers with larger memory have enabled us to do many things that were previously not possible. For example, the advance in neural networks. And then the development of numerical methods have powered the many underlying optimization algorithms that made lots of what we do possible. And the landscape of what optimization algorithms are in use at any given point in time also changed. For example, when I first learned machine learning, second order methods are important. They are still important, But right now, if you are learning the first course in machine learning, given an objective function that's continuous, auto-diff and properly tuned first-order methods or Gauss-Newton methods are great. And people can free themselves from manually deriving derivatives and checking derivatives programmatically right now. And this is different from even 5 years ago or 5-6 years ago, where we were still telling students to essentially check their derivatives numerically so that we know that our models are correct. So here is a very simplified taxonomy of machine learning. And I think a lot of popular press follows this taxonomy. Basically, there's supervised learning where the learning target is known, where there's unsupervised learning where there's a pile of data and you're supposed to discover some interesting things from it, such as clusters or continuous clusters. We'll cover what that means in this class. And also reinforcement learning where the machine teaches itself. A slightly more realistic view is that there is lots of gray space in between these three bubbles. Between supervised learning and supervised learning, for example, the overlap include semi-supervised learning. Some of the labels are observed, some of them are not. And then also what's called transfer learning or meta learning, where you learn on one task can be generalized to another task and so on. We also basically view these broad terminologies as sets of tools and methods. I certainly hope you walk away from this class taking that view, that we learn one method from one particular model, and then the goal is to walk away applying that in to new data sets, and also to use it to construct new models and methods. Okay, I can see some questions streaming in. Very interesting. So we will, at the end, hopefully we'll have time to scan them and make brief answers. In case not, we'll strive to answer on Piazza. So let's, use simple examples to define what we mean by supervised and unsupervised learning first, and then we'll move on to the bigger picture and advanced examples of machine learning. So closer to home is, let's say the task is to predict the price of a house. A curious local economic phenomena in Canberra is the housing market has boomed in the last few years, and especially in the last year during the COVID crisis. And many of the houses on sale in the market does not have a price tag. And obviously valuable, economically relevant question is, how do you predict the price of something like this, right? I captured this example, I think, 2 weeks ago, and the auction is the day after tomorrow, right? So let's say we cast this as a supervised learning task. It contains a data set that contains n samples, x features of the house or data about the house, and y is the price that's been sold. There is public registers of housing, like transaction prices. So these data can be obtained, although not free, right? So let's take the most simplistic view. Let's say X is the area, or basically the size of the building, floor space. Let's first examine how can we predict X from Y, right? The axis is floor space in square feet. These slides are made by Stanford, therefore the area is in American units. If we have, let's say, at least 15 data points, and the crosses denote training point, the goal is basically to interpolate or extrapolate for a house size that's unobserved, let's say 800 square feet, what is the price, right? So we can maybe guess that the price should be around here. Yes. And moreover, we might want to estimate, let's say, like a cloud of uncertainty. If we estimate the price to be around here, there might be upper and lower bands of it. So this is the setup of supervised learning. So in later this week and next week, we will discuss what are the appropriate models for this. For example, should we fit a line on this and then guess the price of the unknown house, or fit a quadratic curve, or something even complicated? What are the considerations for us to decide these, and how do we sort of look at the model to see whether it's doing a good job in various ways? Of course, the world doesn't live on 1 or 2 dimensions, right? We can imagine having a richer set of features, such as the size and the size of the land that predict the house. Then the mental picture for the classification or regression space is 3 dimensions here. Each point lives in 3 dimensions, and we essentially interpolate in 3 dimensions, which is significantly more challenging to imagine. This is also the reason why that in the book, regression examples are almost invariably like 1-dimensional input, right? And we can have even more features, like number of rooms, the year the house was built, its energy rating, and so on. So we can represent high-dimensional features with vectors. I guess the take-home, the high-level message for this slide is we need to get used to thinking about features of vectors and then contextualizing what they really mean in reality throughout this course. I mean, we haven't seen a lot of notation yet, but I do know for a lot of mere mortals, including myself, seeing a busy equation gives people a pause. But rest assured, it gets a little better with practice. So in this class, we'll see lots of vector and matrix notations, as you will see. Right? So predicting a price, which is, we can sort of think of it as a real number, is somewhat distinct from predicting a class of the data object that we're looking at. In the housing case, we can imagine predicting houses versus that are sort of independent structure that's standing on land versus townhouses, which have shared components in the land or sometimes even connecting walls, right? So assume if we observe the housing data like the follows, the x at right. The x-axis is floor space, the y-axis is lot size, like basically the 3-dimensional case that we said earlier. Now we just take the 2-dimensional input space. The goal is to classify or draw a line between the houses and townhouses. Right? We hope there is a clear separation. In this case, there seems is. So we'll look at this in week 2 or 3. And then we can also formulate, let's say, unsupervised learning tasks out of this. So instead of assuming there are 2 labels, let's say houses and townhouses, we now just observe a bunch of points in the 2D space and find some interesting structures. In this, so if we assume there are, let's say, 3 or 4 different type of groups of data in the data set, then this correspond to a clustering problem. In this class, in week 5, we'll look at Gaussian mixture models and k-means. In week 4, we'll look at actually week 6, I think, we'll look at PCA, which is a continuous, one can think of approaches like PCA, continuous dimensionality reduction approaches. So for example, we can imagine, well, depending on the domain and your prior knowledge, there can be 2 clusters or 3 clusters. Which one's better, which depends a lot on the domain and your understanding of the data. I think it's fair to say that there is essentially an add component in clustering, because the objective that's being computed is not necessarily the objective you want in the real world. On the other hand, there is clustering. It's also a domain that's been studied for a long time. There are many criteria, or there are different algorithms that are designed to kind of self-select number of clusters for you. But beware, basically, when algorithms self-select, there is usually an implied what's called hyperparameter that influences the number of clusters and the cluster results you get. So in a sense that despite we could potentially free ourselves from selecting a number of clusters, we're not completely freeing ourselves from tuning the control knob in the algorithm that influences some of these so-called hyperparameters or meta decisions in machine learning algorithms. I'm sure all of you have heard about supervised learning in computer vision. Let's just say that, well, these are covered a lot more depth in the computer vision course. In the ANU, a lot of you are taking the ML and CV master's program, and you will know. So just 2 examples about how one can frame classification problems in rich input data such as images. The first example is image classification, where we aim to say yes or no to particular labels. In this particular example called ImageNet Classification Challenge, the task is to decide whether or not, let's say, if there is a flamingo in the picture. It doesn't care how many, it doesn't care about where the flamingo is and how big it is, right? So this is an image as an input, and then yes or no as an output, and on many different classes. A different problem can be called object localization. Basically, in here, we're not only caring about whether there is the object, but also where it is and where the bounding box is. No, we don't have another example where it classifies each pixel as whether or not it is on the object or not, but that's also possible. So moving on. Machine learning can be also used for natural language. This has also been in the news a lot. Again, machine learning applications for text data is covered in a fair bit more depth in document analysis. In this class, we would not be able to cover enough to essentially allow you to have a proper appreciation of, say, the important domain of vision and language. In the document analysis in the ANU, the course also would not cover machine learning, machine translation as an application in depth. So despite that, machine translation is probably the, I guess, one of the most practical machine learning applications for NLP, aside from also speech recognition, that are enabled in phones and your household gadgets right now. It's actually quite an advanced topic. But the basic setup is that the input is a sequence of text characters or even speech utterances. The output is another string of characters or even speech utterances in a different language. It's a fascinating problem. And in fact, I would say the effort devoted to object classification and machine translation have propelled not just the advance of NLP and computer vision themselves, but also the development of the corresponding models. in the last 20 years or more. So we can say a few words about reinforcement learning, which is like also all the rage in the news in the past number of years. You might have heard of these systems that are showing on the slide. They're all by DeepMind. The first one is computers learning to play video games, Atari games, a collection of 64 games, most of them better than humans. The second one, I'm sure you would have heard about, is computers beating the best of humans in the game Go. The third one is, I picked the AlphaZero cover because the latest one is actually haven't got the cover yet. It's basically the computer essentially just learns to play against itself without being trained by, say, the classic playbook from humans for learning to be the best humans in Go and chess. And the latest one was just released in December 2020. It's called Mu0. It's a machine that trains itself to play with the same representation, trains itself to play across different games, basically Go and chess and checkers and others. So these different systems are increasingly general and powerful, and they are propelled by not only advanced reinforcement learning systems, but also by a massive amount of computation that's available in these large corporations. So what is reinforcement learning again? It is hard to give a mathematically precise and informative definition, and here's a simplified picture extrapolating from supervised and unsupervised learning. So we can view it as the algorithm collects data interactively. Meaning, in the housing price prediction task that we just saw, you are given a pile of data with input and output mappings. In reinforcement learning, you essentially choose what data to collect, in the sense that in the game of Go, for example, you choose which what the next move is, and sometime after that you will observe an outcome, whether the move is good or bad, by either winning or losing the game, or comparing that to one of the known positions that are good or bad. So in that sense, the data collection and training are in a continuous interacting loop. So if you would like to learn more of this, take the advanced AI class next semester. So there are many open challenges in this space for tackling real-world problems. That is to say that solving the games of Go and chess, or AlphaGo and AlphaZero, is not powerful enough to solve many of the real-world challenges we have. And it's also not to say that these computers are not yet capable of, let's say, be the terminator of humanity in a sense, despite what the press, popular press might say. So one common misunderstanding, as mentioned by a few tutors, I think including Alex Solon, who is on the chat right now, is the popular press tend to blur the boundaries between tasks that are sort of in the lab versus tasks that are general and actually useful in our real life. This is not to say that Go is as like mind training game, and intellectual challenge is not useful or interesting. but solving Go and let's say, driving like autonomous cars are still different problems than each other in many different senses. So there's word embeddings is another recent example of machine learning applied to text, which is quite fascinating. It basically maps each string into a vector in a high-dimensional space. It's worth mentioning. So it's quite powerful in the sense that it reveals inherent structures in text that people tend to use. For example, in the toy example drawn here, it's found that the directionality or vector distances in this vector space reflect semantic relationships. In this particular example, capital cities of a country and the name of the country itself. It is trained by just reading lots and lots of text, such as snapshots of Wikipedia. You can think of this as a unlabeled data or unsupervised task. But in fact, if you look into the objective function, what it learns is to basically look at subsequent words. Let's say the slots I'm drawing are 5 consecutive words right now. There are 2 different objective functions in the original word2vect. One is to use like surrounding words to predict the word in the center. The other task is to use the word in the center to predict the surrounding words. And both of them yield similar results. So it's basically using how people write to train the language model. The other interesting thing in the neural network sense is it's actually learning the input vectors of a neural net rather than learning the weights of a neural net. I leave that to your musing. We wouldn't be cover this in detail, but the document analysis class will. Okay, we have about 25 minutes. So I'll move on to cover some of the machine learning projects in and around here. I will start with a project in my own lab. This was done in 2016, a triple AI conference, the top AI conference by Alexander Matthews, who is also around and will be involved in the document analysis class. So what he did was to design the first system to caption images with sentiments. And here are the outcomes, essentially. Learning from a large collection of, okay, what has happened? Did my screen share just end it? Let me just check. Okay, sorry about that. I think my iPad just went to sleep. Yep. Ah. Okay, so this is the outcome. As we can see, the red and green highlighter are respectively the level of negative and positive sentiments that the model assigned to each word. We can see some good examples, such as this, where it's getting pretty good, like it produces a sensible caption with a positive sentiment, right? Interesting cases are, a lot of them are in the negative sentiment, right? So if we look at this particular one, the sentence is very grammatical. The problem is that the description is not semantically logical, or it doesn't conform to the real world knowledge. So the man in the hat is not riding on the crazy horse. And then, for example, in this one, the sentence again is sensible and it's somewhat amusing to read. A happy man flying through the air while riding a skateboard, which is technically true, but it's a kid playing on a playground gadget, right? And then there are ones that, because these models same as word2vec. They are learning a large collection of text sequences. It sometimes violates common sense, right? If you read this, a dead man doing a clever trick on a skateboard at a skate park. It's yeah, doesn't happen in real life. One step further from that, Alex Matthews, again driven another work to learn to capture images from romantic novels. The difference between this work and the previous one is this work is, I would say, more unsupervised in the sense that the model just sees images and a pile of romantic novels rather than having information about whether each word is positive or negative. So from this work, I personally learned quite a lot. One thing I learned is what are sentences in romantic novels like. If you read through the first two examples, it's the red captions are learned from romantic novels and the blue ones are just simply descriptive. It tends to have basically longer multi-part sentences such as this one, or it has parallel structures, forests considered tall and thick trees. And of course, it still doesn't know about common sense, and this is my favorite failure example. That kind of makes sense, and one can argue that it's romantic, but it's not how the world works. Another example that I would like to show you is a network of sequences. So in this example, what you are looking at is the daily view count of YouTube music videos. In this particular case, the blue timeline is the daily view count of Adele song Rolling Deep. The red timeline is overlaid on top. It's the song Someone Like You. So this graph is showing the strength of basically influence of these two videos being recommended to each other. And the rest of the graph shows what are the other songs that are being recommended to Rolling in the Deep or be recommended like, well, have Rolling in the Deep as their recommended list. So we gather this data from YouTube and your favorite video playing platform where when you're looking at a video, it tries to show you another set of related videos, right? So the study of this research are twofold. One is to look at what this network of videos being recommended to each other look like, which was the first paper. And then in the subsequent web conference paper, we improved on the prediction of how we can make use of this network to do better time series forecasting. And what you're looking at is a live system. I invite you to click on the link and go to it. Okay, I'll try not to do this in the lab now. And you should be able to navigate across the songs and really sort of see this system live interactively. And this is also a conference demo paper this year in my lab. So moving on from, I guess, a self-introduction to projects in my lab, I've given you like a sample of 3. In the computer vision lab and the Australian Centre of Robotic Vision, one of the recent projects is to basically learn natural language descriptions from images that will make robots smarter, right? So this particular problem is given a set of videos of people assembling IKEA furniture, can we generate natural language descriptions of that? And the computer vision group have worked hard on that. And you can imagine lots of challenges from image understanding to what kind of furniture is this? And a lot of us would have some experience in assembling furnitures, and there isn't a precisely defined taxonomy about what kind of assembly action there is, despite there might be a finite but large set of components that can be sort of hooked up to each other, right? So check them out. So closer to home, basically Australia is a country with vast span, lots of natural resources, and lots of challenges to manage and make use of them in a sustainable way. So this particular project that we're covering as a sample is called Bayesian joint inversion of geothermal resources, right? And it uses Gaussian process, which I don't think we'll have time to cover, but it's one step up. It's in the book, one step up from kernel methods, which you can read about. So the problem here is geographic exploration is expensive. Basically, we can learn whether or not there's geothermal energy only by drilling a hole in Earth, and drilling is expensive. If we can infer from, let's say, gravity and seismic data, and better predict where to drill, and that will be a lot more resource efficient. In this paper, a number of colleagues from NITA and University of Sydney have shown that jointly using different kind of sensor information, using Gaussian process approaches, have had informative results on this so-called inversion problem. So, for example, Gaussian process is one of the favorite models mentioned by our tutors, Meng Yan's favorite model. And yeah, if you're interested, it's an elegant and excellent model. Another example not only closer to the heart of Australia, but also worldwide now, is to forecast the solar power output, right? So we all know that we can fix solar panels on roofs, but the output of that depends on many factors, like where the house is, where the facing is, but also the weather, not just the long-term weather, but cloud cover at any given point in time during any day. So there's lots of fluctuation and uncertainty of solar output, but on the other hand, being able to forecast and monitor the solar output is quite crucial to being able to manage the electric grid, right? We don't want the electric grid to overflow, and whether a particular segment was consuming or supplying energy is important variables to managing the electric grid. So there are various projects. Our colleagues in the NICTA machine learning team has been working on this since the early part of 2010, and there are some results, and there are many approaches now worldwide. Moving on to the different domain, a number of you, from my knowledge, are joining from different disciplines in ANU, from astronomy to chemistry to biology. So rest assured, there's lots of machine learning applications in these domains, and there are lots of people in the different respective scientific and social science domains who have good working knowledge of machine learning and you are applying it. So I stole this slide from Yuansen Ting from astronomy. Basically, in this example, we now have billions of stars and many billions of galaxies from high-resolution surveys. One example problem that people worked on a few years ago was, for example, classifying stars versus galaxies, and that wasn't a trivial problem. So there are many fascinating problems in astronomy. So if you're interested, read more in Yuansen's homepage. So moving on, with the availability of more data and more compute, models have gotten quite a bit popular, and sometimes they exceeds our expectation to an extent. So remember when I was starting in AI, one of the hard problems was classifying whether a thing is a chair or not. So I picked this example from GPT-3, or the so-called model DALL-E released by OpenAI. It learns from a large number of images and text, and is able to generate images from this description of an armchair in the shape of an avocado, which is quite fascinating. It does know what a chair should look like, which is fun. But on the other hand, it's also concerning because when the data is that big, yes, it can generate interesting, fascinating results, but sometimes it also has hidden biases. I'm not sure how well, given the delay in the display that we're seeing, I'm not going to try and play the video that we're showing here, but I highly encourage you to watch it. So here are a few examples of machine learning bias in reality. So Latanya Sweeney is a professor of law in Harvard University, shown on the slide here. So she was I think she's arguably the first to identify and articulate the problem of large-scale biases of machine learning that's being deployed. So the video goes by her saying one day she was sitting in her office with a reporter searching for her own name. Suddenly, there are search engine results that suggest that she has had an arrest record. That was very surprising. And she has never had been arrested, of course. But she dug further and found that the reason for that, or the apparent phenomena, is that if you search for a name that's traditionally given to African American or Black person in the US, the Google ads would pop up like entries related to arrest record, which is very discriminatory, right? And not only that, people have subsequently found that searching for Black names will give you predatory ads from credit cards that is predatory, give you high interest, and also give you entries such as how to clean up your credit history and so on. So moving on from that example, another famous example in 2015 was a Haitian software engineer posted an example on Twitter saying Google Photos are classifying his friends who are dark-skinned as gorillas, and that's terrible. And a few years later, as Wired report, like there has been lots of press on this, Google still hasn't solved the problem, and it simply does not classify gorillas. One may argue that some of these problems are from training data, but training data alone is never a sufficient or an adequate answer, right? You can say that, well, take for an example the online facial recognition database called large LFW, or labeled faces in the wild, that's been used to develop lots of machine and benchmark machine learning algorithms for faces is mostly white. Black faces are underrepresented for historical reasons online, but that's not an excuse for not being able to classify Black faces properly. More recently, so this paper was posted in December, and echoes well with the GPT, large language model. It's done by, researchers in all the main, like large corporations, academia alike. What they have found is that you can actually extract memorized training data from large language models, GPT, i.e. And they have devised a series of reverse engineering techniques to check what kind of training data are memorized. For example, people's phone numbers and addresses, which are arguably privacy sensitive. As an anecdotal example, they found that like Donald Trump's Twitter ID was memorized, and then like WikiLeaks content was memorized. So this is dangerous. If companies use their private data to train machine learning model, then apply the model to some tasks, such as whether to give you credit. So using this approach, you can actually recover private data, such as people's banking record and credit history, from just the model without seeing the training data. This is very concerning. So in this last 5 minutes, I've been talking to you about the concerns of fairness, accountability, and transparency in machine learning. I would just go on to say that there are ongoing efforts to address that, and there is one at the ANU that I'm personally involved in. So it's called the Humanizing Machine Intelligence Grand Challenge. The research addresses a broad spectrum of issues in this space, and there are researchers from philosophy, social science, law, as well as computer science, right? So, like you can read, if you're interested, go read the discussions of these broad research themes such as automating governance, personalization, including social media and recommender systems, algorithm ethics from planning to theoretical concerns to other topics, and also human AI interaction. How do we build effective partnerships with robots so that they don't kill us and we sort of work more effectively with them? Moreover, there's a public-facing component of the HMI project. So there is a seminar series that's being run and archived on YouTube. So if you go on the website, you should be able to find it. You can have a taste of what issues is contemporary to being covered in research seminars, such as importance of modeling data missingness, resolving fairness, and role of computing social justices. Okay, so back to our simplistic picture of supervised, unsupervised, and reinforcement learning. I hope these examples give you a sort of nuanced flavor about what's possible among these. Moreover, there are other machine learning tasks, such as active learning, which is similar but distinct from reinforcement learning, that it chooses which data to learn. It doesn't necessarily consider action spaces. For example, Meng Yanzhang, one of the tutors, PhD thesis is in this space, in multi-armed bandits. There is what's called transduction, using some of the text data to build models, estimation with missing variables, and code training, and many others. I'm going to use this next picture to illustrate the breadth of machine learning as a subject matter right now. I took these keywords from Europe's call for papers, the top machine learning conference. So if you read these keywords, you can say that I roughly classify them into topic areas, from theory to like asymptotic analysis, models, some of them we will see, methods, basically how do we optimize them, learn these models, and problem settings, and different application domains. I would argue that no one single course nor a single person have the breadth to have in-depth understanding on all of them. So don't feel bad if you encounter a machine learning term that you don't know. We all have that all the time. This is also to say that machine learning is a fast developing field that tend to come up with new names that are sometimes ambiguous with other fields. For example, policy in reinforcement learning means different things than policy in government. So there are many new names, and sometimes like one of the missions of this class is for some of these new names or sort of terms uncover for you what the underlying mathematical formality really is, so that you can make connections and apply this to your new learning in the future and not be scared about new names. All right, so what this class will not cover is we won't talk about reinforcement learning. We won't talk about time series and graph in depth. And exception is either Markov model and sequential model towards the end of the semester. We won't talk about recommender systems, and neither will we talk about optimization in depth. Take AML if you want. We will not talk about machine learning systems or your trendy deep learning package. So most of the assignments are done in NumPy or asked to code a component in order to understand it deeply. So I think people have said that this class is hard, but we will use this as an example to show that there are harder ways to learn, or us sitting at the comfort in front of our desks learning math, well, may not be so hard in perspective. So if you haven't registered on Piazza and Grayscope, register for a tutorial slot starting in half an hour, and look at assignment 0. So yes, we have 3 minutes left until 11:30. I'm happy to invite questions.
Hi, I want to know if there is online session for the lectures.
So as I said, we will, so this is a lecture slot, and we will also do a Friday, what we call workshop slot, because we really mean it to work sort of in connection with the lecture recordings.
Okay,
you can treat it as a lecture slot, but as we will tell you on Friday, or I should say this now, so there is in my view, a unit of machine learning knowledge, like let's say oversimplistically, it covers 2 parts. One part is the mathematical formality, how you get to a mathematical conclusion. The other part is the story, the motivation, the intuition, and about, for example, why do you want to use linear regression, and right, how does it connect to other methods? So I would say that, and also from previous years' feedback, that the balance of these 2 parts are sometimes a bit off in the lecture recordings. So we will try and sort of provide you a different view or mitigate that. So for some of the sessions, we might cover like some of the derivation, the mathematical formality in more detail. For some other sections, we might start with a longer run about why and the story, essentially. I hope that helps.
Yeah, sure. So what you mean is like that lecture and workshop is combined, and they're basically the same thing, right?
Yes. Yes, if you want to view these workshop sessions as lectures, that's, yeah.
Yeah, sure. And and we also have the lecture recordings, right?
Yes.
So maybe we should like watch it before the workshop.
Oh yeah, if you can do that, that will be excellent.
Sure.
And I'll tell you, basically in the workshops, I strive to strike a balance between, say, the book's ways of presentation and the lecture recording slides. Sometimes they are different, sometimes there are gaps. I would also say that going back to the book, as you can see, there are exercise questions in the book that are specified in the class homepage. So the style of the book, textbook, is written such that the exercise questions are more for completing the gaps or filling in the gaps of the book's mathematical logic, rather than to test your understanding applying the method to something else. So if you don't if you find the exercise difficult, don't blame yourself. They are a lot of times difficult. And I would say our exams are not very similar to the exercise in the book. So they are for references. Right. So a question just came in from the chat. So in the book, as you will notice, in some of the exercises, they say they are on the web, right? So on the book homepage, there's a section for extra materials. You can download a PDF with some of the solutions. For the others, they are not openly available online. I'm right now reading Rachel Baker's comment on Teams. Okay, open book learning. Okay, thanks for reading Grayscope document. Yes, we plan to have open book exams and quizzes. No, we do not plan to do a lockdown browser exam. That's hardly possible with half the class remote, and I think lockdown browser exam is more appropriate for like first year programming class, for example. Yes, okay. Training data with mislabeled points, which is not a question I can answer in 1 minute here. Basically, yes, there's a large number of research literature about that. Yeah, maybe we'll take this one offline. Any other questions? Nope, not at this point. I think it's worth saying that as I announced on Piazza, I plan to essentially hold contact hour between now and noon on a weekly basis. And this week, I will just keep the recording running. In future weeks, I plan to have the office hours off the record to encourage people to ask different questions, because this week's question are mainly about how the class will run, so it's worth having it in like recorded and available for everyone. So there is a question. Okay, Noel hinted us, why aren't the workshops being recorded? So in short, the main workshops are recorded. Yes, whenever I hold them, I intend to record them. But the half an hour between 11:30 to 12, which is not on the timetable, are not recorded. Where is assignment 0? It's in. Okay, let's see if I can find it in the overview page. It is in the Piazza post, and also in here, there's a link. Yeah, in the prerequisite slides. Okay, someone answered. Will programming problems appear in final exam? Great question. The short answer is no. Given the time constraint of roughly 3 hours, we'll work out how exactly that works. Whether across different time zones, it's a big challenge of deciding an exam schedule that works for everyone. If we make it longer, say a 12-hour take-home exam, then it will bleed in and overlap with your other exams. But we intend for the final exam to be bounded in time, roughly like 3 hours. I feel that it probably would not be possible to ask you to do substantial programming in that time. And I also believe that the best programming is done without a hard time, like a tight time constraint where you can look up online and also write better code that way. Ella is asking a question. Oh, okay. That's a link to assignment 0.
Hi.
Yep.
About the two assignments, are them very long, or need us to spend on them about half a semester to solve them?
Great question. Yes, they are. I would say yes, you are expected to devote substantial time. I have assignment 1 draft is almost done. I would not be able to give you an estimate about how long. I would say if I were doing them, I expect to spend more than a day in the best case. If I see each question and I sort of try a little and be able to solve it, then writing and it's basically typing up the code, the debugging the code, making sure the sort of outcome is what I needed. It will take, I think, more than a day if I'm just sitting there working on it full time. And furthermore, so the assignment submission is on Grayscope. We basically the tutor team, Alex Owen, has made a test assignment that basically allows you to debug your Grayscope programming assignment output upload. Basically, another thing that Grayscope allows us to do is to partially auto-grade your like simple assignment and multiple choice questions. So in that case, your it's highly recommended that you also try the Grayscope upload, watch the tutorial video, and then try the test assignment when it's released, also next week. And I hope that helps. And the test assignment shouldn't take long. It's mainly, again, test your, you know how the Markdown cells works and your Python version is correct, because Grayscope is a bit more strict than that. Good.
All right, thanks.
Yeah. Good question from Ella Wang in the chat. What will the difference be between lecture recordings and workshop content? So I would say lectures in the previous years, they are designed to give a more or less complete narrative about what you are trying to, what you're supposed to learn. Right? So I would try less of that, but more of filling in the blanks either in the derivation or the story side of the material. Lecture recording last year was done by Echoes 360 in classrooms, so they will have slides but no talking head, if that makes a difference. And also student questions in the lecture recordings are often not audible, and a lot of the times the lecturer did not repeat the question before answering it. So just, yeah, bear that in mind. So it's up to you to choose what to watch in a sense. For example, in our Friday section, I have chosen to spend more time on Gaussian distributions, an object that maybe all of you think you know it. But some of the intuitions I would argue is sort of underappreciated, such as what a two-dimensional Gaussian covariances really look like. What's the geometric intuition of that, which is crucial for a number of things that we will subsequently cover. So in that sense, I would also argue that that many of the intuitions or like basic mathematical tools is less appreciated than it is. In other words, chapter 1 and 2 of the book covers all of them piecemeal, and we will scatter these quote-unquote prerequisite material throughout the semester to give it some emphasis. I do feel chapter 1 and 2 are actually quite important. Not all of them we will need or cover in this semester, but there are parts that are good. Guang Chuang Liwen asks, for the assignment, is an expectation that group of 2 students higher than that of a solo student? The short answer is no. We will all use the same grading rubric for a group assignment versus a solo submission. I feel the idea is really to give people an opportunity to work together and talk to each other. For some students, flying solo is actually better than like teaming up with another people or having the collaboration overhead. It's your choice. That said, we will pursue plagiarism. I hope. So basically, the protocols of working on assignments are the same, but this is a advanced class. I hope everyone is familiar with that already. People can discuss the assignment, but they are expected to write up their answers independently and not lift from the internet somewhere, even if you find it verbatim. Otherwise, we will look out for those cases. And yes, your assignment is expected to be your work. And in a real video assignment, you will explain some of the workings of your assignment and how you arrive in that solution. There are certain challenges of delivering such a course in large scale. For example, other similar courses worldwide will have a project component, but at the class size of 200, unfortunately, that's not quite feasible. Dian Jiao asked what the video presentation assignment will be like. There is a brief spec on the assessment webpage right now. We will release more guidance closer to time. And the video assignment is not due until the last week of the semester anyway, because we would want you to have done the 2 assignments in order to choose your topic. Of course, you can choose to do your video assignment earlier on the contents of assignment 1, subset of assignment 1 anyway, and that's up to you. So stay tuned. I can hear some people typing in the background. I think all of the questions about logistics. Good question in the chat. Video assignment is an individual assignment. As we said, let's go to the course webpage right now. Yeah, a video assignment is an individual assignment. Even if you have done written submission, written and programming assignment together as a team. Each student are expected to do the video assignment individually, right? If you have done the assignment as a team, just pick a part. I say pick a part because the length constraint of the video is between 4 to 8 minutes. Pick a part and then talk about how you, like the collective you, arrived at the solution. And the thinking behind it. Right. Yes, you can choose to present what you have individually contributed to your team assignment, which will not affect your assignment score, or choose some other part to talk about, for example, one question of the assignment in depth. For example, assignment 1, the theory part or the mathematical part is about Bernoulli and binomial distributions and beta priors, or basically coin flips, and deriving what beta prior is. And the practical part is about Bayesian linear regression and neural networks. Each of those have several tasks and separate questions. So, for example, you can choose to focus on your implementation of Bayesian linear regression, the hurdles you ran into, and your interpretation of the results, or something else, or you can choose to present the neural network part. We expect to make a few broad suggestions, but it's really up to you to choose.
Thanks. Excuse me. For the video assignment, I think so I can present and deliver some idea inside it, and even though it's not mainly the part of my job in the assignment for the group, so I can also explain it as in the video assignment, right?
Great question. We haven't specified that. I will make a note and make sure that we allow people to go a little bit above and beyond what the assignment was requiring. If, assuming what you talk about, we assume what you talk about is relevant to the assignment topic. Let's say Bayesian logic regression neural networks, or say beta priors for assignment 1. You can go a bit step further, I feel, if you say, I then have whacked my approach against this really cool data set. Then I think that is fine. You can also choose to talk about numerical issues, which is not a focus of this class, but they are very important, right? For example, for vanilla linear regression, the textbook says, here's a formula. And it says, well, you run into numerical issues if you just do the straight inverse, which I think your implementation would do, but, well, not for patient. But, and you can talk about how to avoid that. If you do that sensibly, I think you should get credit.
Okay, thanks.
Yeah, thanks, Guishan, for the question. Yuan Yuan Wang asked the question, should we enroll the same tutorial to the teammates? I think that's been asked earlier, a little bit earlier. The short answer is no. These are two independent processes. Okay, we are 10 minutes to 12. If, don't feel compelled to fill like all the question slots. And as I also know that the office hours tend to be very much underpopulated until the very, just before assignment due date or just before the exams. Going to go back to the Teams. Oh, just a quick note about, yeah, I guess online tutors, labs, and workshops. I think it will greatly help the rest of the class and us is that when you ask a question, turn your video camera around. When you're speaking, turn your video camera on if your setup allows. I think people will all appreciate that. Okay. If there is no more questions, I hope you enjoy the rest of the class. And I will see you next time. Meanwhile, enjoy having a go at the first tutorial and assignment 0. All right. See, Ella said, okay, yes, if you enroll in one tutorial, can we drop into other tutorials? The short answer is in-person tutorials have a strict limit of 20 persons due to COVID. So you can try dropping in if other students, like counting on some other student not showing up, but prepare to be turned away. For online tutorials, there's not so much of a constraint, but we would certainly appreciate not like 50 people flooding the same online tutorial session and overwhelming the tutor. If that happens, we'll shout at you. And of course, people who officially are in a session slot have priority. Yes, the Friday workshop is at 12 instead of 9. I will see if I can get the timetable information changed. If not, we will just make it a sort of a convention agreed upon within this class. Because at 12 it does officially overlap for half an hour with the subsequent tutorial, which is less than ideal, but it feels better than making half the class get up at 6 a.m. to do this workshop. Okay. For 5 minutes before, feel free to go. If you have nothing at 12, I think our questions are trending down whenever I say we're about to hang up. Like it comes in small bursts. Yep, thanks everyone. I think we're done. I will stop the recording. Thank you for your appearance in the online lecture too.